First of all, thank you for blowing my mind completely. I am so curious about everything now. I don't know where to start. But I guess I will. My first question will. My only question will be for Dr. Fries. And I don't even pretend to understand anything of what you talked about. But I do listen to NPR, and recently I was listening to the fact that the universe is expanding faster than the speed of light. I'm the guy in red, and no hair. Faster than the speed of light, which means that the light will, if it's expanding faster than the speed of light, the light will never reach us. So the question, and I don't even know if this makes any sense, but is it possible that what we think we see as the horizon of the universe is not the horizon of the universe, but the horizon is further away than we think because the light is just not reaching us anymore?
It's kind of the opposite of what you're saying. So if you, but you're onto something. So the size of the observable universe is set by how far. What is the distance to the thing? The light could have gotten to us within the age of the universe. So there is a fixed size to that. And because the universe is now accelerating, which it wasn't in the past, but it is now, that means that this horizon size, or the size of the observable universe, is actually shrinking. Things are accelerating away from us, out to where we will never be able to access them. So right now is the largest amount we can ever know about the universe. Well, unless something changes that we can't anticipate billions of years from now. So the moral of the story is build telescopes now. We're losing information.
Okay, thank you. Yes, there's a question here too.
My question is an add to this one. In the very early, I don't know, picoseconds or something like that during this inflation phase or whatever it's called, I think the present model says the expansion was much faster than light can actually be. So is that, can you comment on that? I mean, we learned from Einstein, there's, for matter, you never ever can reach the speed of light. And how does it match?
Yes, we think there were, in the very, very earliest days of the universe, very, very early on, there was another accelerated phase of the universe that we call inflation. And so that's very strange. We had acceleration very early on, and here we have it again, and we don't know how, if and those two eras were in any way connected. We don't know that. But when we say the expansion is faster than the speed of light, that doesn't mean information is transmitted faster than the speed of light. So it doesn't violate anything that Einstein tells us. It's not, so the underlying space-time expansion doesn't mean that you're getting information too quickly. So there are no contradictions here.
There's another question next to, yeah.
Ulrich Walter, as far as you can see, the dark matter investigations in the crisis, because having looked for decades for it, you didn't see anything. So what is your option? What are your options? If it's not matter, what is it?
We do believe it is some kind of fundamental particle that we haven't yet discovered. And in the search for WIMPs, there has been a search now for about 25 years, but that doesn't mean, but we just haven't. In fact, some of these experiments have anomalous results, and so we may actually be sitting on the solution. We don't know. So it's going to take, if it is this one particular direction of these weakly interacting particles, we still have a ways to go as far as future experiments to test this hypothesis, so we don't know. Of course, there are other alternatives, and there's another very good one, which is called the axion. In order for a candidate to be a good one, there has to be more than one reason for its existence. So these two particles, the WIMPs and the axions, are automatically there in particle theories for reasons that these theories were invented for reasons that have nothing to do with dark matter. But and so the axion is an outgrowth of something in the theory of strong interactions where you automatically would get an axion, and people are looking for that. So I think the time frame for these things is within the next decade. We really hope that it's if it's one of these two that we're going to find it.
And if not?
Then we move on.
Okay, I think we have to take one last question we had up there. Yes. Yeah, okay, we have two last questions, there and there, yeah. Okay. Sorry.
Thank you for great talks. I have a question for Dr. Marshburn. You listed a lot of problems with human spaceflight. What do you think is the most challenging problem with traveling to Mars?
This one's working? Yeah. It appears to be radiation. And either a willingness to accept the risk of higher radiation doses when we go there, or ability to protect the human body from the radiation. One of the solutions that many in the audience or some have worked on is just getting to Mars faster, having better engines. You can even induce an acceleration, feel like gravity, 1G even, and then turn around and brake on the second half of your trip to Mars and have a 1G deceleration. So you can solve a lot of problems with spaceflight depending on the vehicle. Pending that though, right now we're just trying to understand exactly what the radiation is and what the effects on cells and the human body is. So I don't feel like it's insurmountable, but it's a big one. We'll be taking some risks when we go to Mars. The other thing is the problem that we don't know yet. The eye problems we have, that's a substantial one. And I think we just need to spend more time in low Earth orbit, more humans in space to uncover things we just hadn't even seen yet. That could be a human risk for going to Mars.
Okay, thank you very much. And the last question now.
Hello. We know the laws of thermodynamics. But what do you as physicians or physicists say about free energy as Tesla talked about?
I don't know. Free energy.
Is there not is there an answer in the panel? We have a lot of professors here.
Well, there are many quantities in thermodynamics, and free energy is one of them. So, for example, in inflationary cosmology, the potential energy that's driving this accelerated expansion, you can think of that as a free energy. So there's these thermodynamic quantities. Yes, they're there.
Yeah. Okay,
Yes.
Okay. So, thank you very much for your attention.
Yes. I just wish to conclude by thanking my co-chair, Dr. Dunbar, and to thank all the speakers on this session and the audience for great questions. Thank you.
Thank you very much.
Thank you.
Thank you.